thought I had finished out these videos, but I went back and realized I hadn't done the last two layers, the internetwork layer and the data link layer, and I know it's about 2:15 right now, so many of you may or may not be able to watch this. I'm going to try and have this up ASAP. This should be all one video. So the internetwork layer, this is the layer where most network technicians do their work, where most, I guess, administrators do their work. This is the layer that routers forward packets. Okay, so so packets are what we're dealing with when we're talking about encapsulation at the internetwork layer. The four main tasks of the internetwork layer. So define and verify IP addresses, right? So when you're talking about from endpoint to endpoint, it's where the packet is created. On the source, right? That's where the destination IP address and the source IP address are added. And at the receiving end, that's where the IP address is verified. It says, does this match the IP address that I have configured for my PC? And if it does, it hands it up to the next layer, to the network, to the network software or the transport layer in the TCP/IP model. Okay, so this is the layer responsible for that. It's also the layer that is responsible for routing packets. So this is where routers actually function. In other words, getting packets from one network to another down the line until it gets to its ultimate destination network, right? Because we know an internetwork is actually just a collection of multiple networks. It also resolves, this is the layer in which ARP occurs. That's where MAC addresses are resolved for IP addresses, and efficient packet delivery, okay? That has to do with how packets are routed. It's looking for the most efficient routing method, okay? So let's look at these tasks in a little bit more detail here. Oops, hang on. There we go. Okay, so defines and verifies IP addresses. So that what I was mentioning, there's sort of two purposes for an IP address. First of all, it defines a network in general, or a network device at the internetwork layer, and it also defines, it defines a network itself, a specific network, and it also defines a machine on that network. So there's two parts to an IP address. We're going to look at IP in a lot more detail in chapter 6, which I should be able to have uploaded by Thursday. But we're going to look at IP in much more significant detail than today. But so an IP address has two parts that it identifies. It identifies a network and it identifies a specific computer on a network. Okay. When a device receives an IP packet, it compares the destination device with its own. Again, at the internetwork layer, we know that this happens at the network interface layer as well. So the network interface or network access layer is receiving a frame identifying the MAC address and handing it up if it matches, right? The same sort of thing happens at the internetwork layer. The internetwork layer looks at the packet though and says, does this IP address match my configured IP address? So if it matches, or if it's a broadcast, then the packet is processed. If it doesn't match, then it's discarded, okay? Same sort of thing that happens at the network interface layer or network access layer. The next thing that the internetwork layer is, of course, responsible for is routing packets through an internetwork. So routers have the job of figuring out the best the best route on which to send a packet as it travels from network to network to network, ultimately to its destination network, okay? So packets, we've mentioned that IP addresses identify two things. They identify a network and they identify a host on a network, right? And so the routers actually use the network ID portion of the IP address and their routing tables. They compare that to their routing tables in order to determine the best path to the destination. So the best way I can sort of break this down is to sort of think of the analogy of a zip code, right? Your routers are your post offices, and your zip code is how they determine the area or the correct post office to which to send it. So each post office is going to cover a number of zip codes. Those would be the networks that post office knows about. But they can communicate in different ways about the networks that they know and how to get there. So routing tables can be built in a couple of different ways. They can either be built automatically or dynamically, or statically or manually, essentially. So automatic, dynamic, manual, static. So you can build them in a number of different ways. We're going to look at routing protocols in more detail in Chapter 8 of the next class. So if you're more curious about that, take that class. We'll delve into that in more detail. But routers, essentially, they have a routing table, and they're going to use that as well as the network ID portion of an IP address to forward packets to the correct networks. Okay. If you think again about the analogy of the post office, right? The post office in our area covers, I guess, let's think about the post office downtown Prescott here. This covers 86301, 86305, 86303. And so on and so forth. There's probably 2 or 3 more on that same list that our post office covers, right? And so if a package comes into our post office with the destination zip code of 86301, they know that that's going to go to the area north of Gurley Street. 86303 is south of Gurley Street. And I don't know the exact division. I just know that one little one. So they know how to route that packet, if you want to think about it like that, based off of the zip code. They get it to the specific device using a different method, of course, or the specific home using a different method, but the zip code just points to our post office covers these networks, if you want to think about it like that. Your router covers these networks that are directly connected to it. That's how you have to sort of think about how routing works. And oftentimes in a larger internetwork like the internet, there's going to be multiple paths, multiple ways that it can go to get from point A to point B. If you want to think about the analogy and take it even further, it might be more efficient for some mail to go on a plane and get to Prescott, Arizona, or it might be more efficient to put it on a 18-wheeler and drive it up here. So it all depends. So maybe not directly to Prescott, Arizona. I don't know. The analogy is not perfect. Just think there's multiple ways for a letter to get from, let's say, I don't know, China to Prescott, Arizona. Just in the same way that there's going to be multiple ways that you can get a packet across the internet. So routers would determine it's not flawless, obviously, but they try to determine the most efficient path. And the internetwork layer determines the best way to get a packet from network to network. That's really what it comes down to. Okay, every frame, of course, at the lower layer contains a source and destination MAC, as well as the packet, which is encapsulated by the frame, a logical IP address, right? So a physical MAC address and a logical IP address. So every frame has to have both of those to be completed and ready to send on a network. So when the packet's ready to send, the destination's MAC address, the destination device's MAC address within your network. See, MAC addresses don't go out of your network. So the destination device, if it's outside your network, is going to be the router, your gateway's interface, right? That's what's going to be the MAC address on the frame. Okay, it's the internetwork layer that's responsible for using ARP to resolve. It knows the IP address, right? It's going to send it out. It knows the IP address of your gateway because that's listed in that information. So it's going to use that in order to send an ARP. An ARP goes out as a broadcast frame that says who has this IP address. And one network interface card, whether it's the gateway, whether it's a device on your network, is going to respond and say, I have that IP address, and here's my MAC address. Okay, so that's how address resolution works. So we talk about that more later in the chapter, but that's in a nutshell how it works. I think we have a little demo that shows it, but we'll get there. And then efficient delivery. So of course features like flow control, confirmation, message assembly, none of this is done by the internetwork layer. That's all handled by the TCP/IP. I'm sorry, by the transport layer, the TCP part. So that's all handled at a higher layer. So and it's the same sort of thing when you talk about how Ethernet is a best effort delivery system. It's all about just sending it and hoping, and really no other effort goes into delivering data when you're talking about Ethernet. The same could be said for IP or network internetwork layer protocols, right? They're just focused on getting it from point A to point B efficiently, right? It's considered a connectionless protocol. In other words, it doesn't establish any kind of communication first. It just puts the addresses on there, encapsulates it into a packet, encapsulates it into a frame, and sends it on its way. Okay. So again, upper layer protocols, the transport layer protocols, are what ensures that if a packet didn't get there on time or correctly, that it retransmits that. Okay. Protocols that are in use at the internetwork layer: IP, that includes IP version 4 and IP version 6. We're going to delve into these in a lot of detail in the next chapter. So these are really information heavy protocols, and we dig into these, especially IPv4. It's very important that you understand that. That's one of the primary topics. I'll probably do a video on that, but I'm really going to focus on discussion in class as well. That's why I haven't released videos on that yet. I will most likely do a video on IPv4, at least subnetting, so that you guys can go back and review it. But I'm really going to try and focus on digging into IPv4 tonight. And so ICMP, we know, of course, is for essentially testing a connection, right? When you send a ping message, that's actually sending 4 ICMP packets, known as an echo request, and echo reply is what you receive back. Echo request just says, hey, are you there, essentially. Echo reply says, yep, I'm here, I'm good to go. There's a couple of errors that can go wrong with an ICMP that would tell you different things. Things like destination host unreachable. That's when a router says, I don't know how to forward this, so I'm just saying as a courtesy, no can do. And then there's request timed out. That's, you sent it and nothing ever came back within a certain amount of time. Destination host unreachable, request timed out. General failure, general transmission failure, that usually indicates that there's something wrong with your IP address settings locally. So there's a couple of different errors you can get when you send a ping message from Windows. Then you have ARP. ARP we've talked a little bit about. We're going to really talk about it in more detail now in just a minute. But and then IPsec, IP security. That's an IPv4 protocol that's designed to encrypt a packet so that the packet itself is encrypted. Encryption typically happens at higher layers in the TCP/IP model. So typically when you have like a secure protocol at the application layer, that's where your encryption occurs. IPsec just moves that encryption down a few layers so that it's encrypted at the packet as a packet itself. So IPv4, it's in the form of dotted decimal. Dotted decimal just means essentially, it's written as 4 numbers separated by dots, 32 bits in total. So each octet is what it's known as. Is 8 bits in length, so a maximum of 255. That's the highest you can go with 8 bits. So we'll look at this in far more detail in chapter 6. So just be prepared for that. We're gonna really delve into this. In an IP packet, you have these fields: version, time to live. Time to live is like a timeout that says if it doesn't get to its destination in this amount of what's known as hops, essentially routers, then it will discard the packet. That's for the sake of preventing packets from going on and on and on and on and on forever in some kind of routing loop. That is a possibility with full meshes especially. So if something doesn't know where to send it, it just keeps forwarding it in a circle. Eventually you want that to expire and get thrown away. So that time to live is to prevent a routing loop. That just goes on forever. And then you have the protocol. This is in relation to, I think if I'm not mistaken, that's talking about the protocol, the version of IP. So whether it's IPv4 or IPv6. Then you have a checksum similar to the CRC in a frame, right? That would be at the, this would be in the header though, so not in the trailer like it is on the frame. So this would again be run at the sending and receiving device, the receiving device. It runs a checksum on the frame, says okay, the frame's good, but then it forwards it up to the internetwork layer and says not so good, and then it'll discard. So that checksum is just to keep error data from going through. Then you have source and destination IP address. Okay, source IP address would be the IP address of the sending device. Destination IP address would be the receiving device on the very end of the connection. Not like the MAC address where it's, you know, if it's going outside of your network, it's the router's MAC address. That's not what it is with IP. This is the IP address of the actual computer at the destination. Okay, and we'll look at that in a little bit more detail as we move on. Now IPv6, it's significantly different than IPv4. It's broken up into what are known as fields. Each field is 4 hexadecimal characters, or a total of 16 bits. 16 divided by, I don't even know exactly off the top of my head how many fields. I apologize. I believe it's 12 total fields, or 128 bits. I think that's right. Might be. Oh geez, I'm having a hard time remembering this. Don't worry, I'll know by the time we do chapter 6. I'll brush up. Anyways, IPv6 is significantly different. It's a far, in some ways far superior, in some ways far inferior because of the difficulty, I would say. Though some people say IPv6 is less difficult because they just built in a lot of things that they didn't build into IPv4. IPv6 was developed in an attempt to prevent a problem with IPv4, which was if you only have 32 bits of addressing, then you quickly start to run out. Essentially, there are in total, I can't remember the exact numbers, but somewhere in the billion range, like 4 billion IPv4 addresses. We're going to talk about this in more detail in chapter 6, but essentially IPv6 was designed to alleviate this problem. With IPv6, there's enough addresses, so when it talks about larger address space, there's enough addresses to give a unique IPv6 address to every single human being's entire body worth of cells. So like if you were to give an IP address to every cell in your body, that and every other person in the whole world. So 7 billion people, however many trillions of cells each person has, would each get its own unique IP address. So it's significantly more, let's put it that way. There's also a hierarchy to how it's laid out. There's somewhat of a hierarchy to IPv4, but the hierarchy in IPv6 is a lot more thought through. And in fact, they initially designed the hierarchy to work even more regionally. So like they were going to say, okay, Prescott, Arizona would have its own chunk of IPv6 addresses that they would use, where that kind of got thrown away pretty early on because IPv6 was actually developed in the 90s and it's evolved quite a bit. But there is a hierarchy to it that's a little bit more of an improvement on the hierarchy to IPv4. Also, auto configuration, there's a number of different ways. We know IPv4 has auto configuration as well, known as DHCP. IPv6 has auto configuration that we'll talk about. Basically, a router would configure your whole network without the need for DHCP. Then you have built-in quality of service support. Quality of service is typically discussed when you're talking about IP phones. So quality of service essentially flags data that says this is priority, this is not. So support for mobility, this is for used with mobile networks like LTE networks. So this supports that. Of course, IPv4 has developed. Now, all of these things IPv4 has sort of addressed, and so that's why it hasn't gone away. But I don't know. Extensibility just says they haven't even gotten close, even with the hierarchy, to using anywhere near the addresses. So they've used like less than 1% of 1%. So we're talking like nothing. As far as what's actually been used. And they have all these other ones that they can use. So I think IPv6 is sort of developed with a more futuristic perspective than IPv4 initially was. So there are certain tools, utilities, that allow IPv6 to run alongside IPv4 without needing to make any big changes. And in fact, ever since Windows Vista, IPv6 has been built into all of the mainstream operating systems. So even with Mac OS, Linux versions, everything supports it. Nobody really uses it as far as like mainstream. I mean, it's used by a lot of WAN providers for different purposes, but typically you don't see it a lot in LAN implementation. So there is need to learn it, because I think within the next maybe 30 years, I don't know, if some of you guys might be in the industry long enough. I doubt that I will. I mean, I'm young, but I don't know how quickly it's going to go away and transition from IPv4 to IPv6. There's been a lot of pushes within the last, I don't know, 10 years or so to really make the switch. But that being said, it's slow, and they're doing everything that's happening is always like with the mindset of like, okay, let's make this as easy as possible for everybody. So you guys learning this now is going to be really handy. And if you, of course, are planning on getting the degree, you're going to need to know how to do IPv6, because the Cisco, the CCNA classes really delve into this stuff. Again, it is important. I don't want to diminish the role of IPv6, but it hasn't really caught on yet. So, address resolution protocol. I've talked about this with a number of you guys privately. I've talked about it somewhat in class, but what it comes down to is it's designed to resolve an IP address to a MAC address. Okay? A known IP address, right? At the internetwork layer, it knows the IP address. When you type ping and then an IP address, it knows that IP address. When you type, or for example, the gateway. Suppose you're sending a packet outside of your network, but you don't have the MAC address of your router. Okay? It would look at what you have for the IP address of your default gateway and generate an ARP message that says who has the IP address that you have listed for your default gateway. Okay, and then your default gateway would, of course, reply with its MAC address. So it works across the board, regardless of how you're sending your data. Now, every computer has a list of MAC addresses and IP addresses. This is known as an ARP cache. You guys have seen this because you've deleted your ARP cache in previous labs, right? You've done ARP-D. That deletes the ARP cache off of your computer. ARP-A shows you the ARP cache, right? So what happens is when you go to send a packet, if it doesn't have a destination MAC address that it can put on there, it sends out a broadcast frame, an ARP broadcast frame, that requests a MAC address corresponding with the destination IP address that you have on your packet. Okay? And one device replies. It puts that MAC address as its destination on the frame, puts its own as its source, and adds it to the ARP cache. Okay? That's what happens. That's it. That's the whole process. So it's a very important protocol because it happens all along the way. ARP is used at the internetwork layer for finding not just MAC addresses, but other types of physical addresses. Typically, MAC addresses are used even in other types of technology that don't necessarily use Ethernet. MAC addresses are still the common physical address. Okay, so ARP, of course, is used at the internetwork layer. It just says who has this IP address and gets a reply. Okay, that's really it. And again, I mentioned there's an ARP cache stored on every computer, right? This is just a temporary storage. When you shut down your computer, it has to rebuild it, but it happens very quickly. Okay, so as MAC addresses respawn, or as computers respond with their MAC address when ARP broadcasts are sent out or ARP requests are sent out, it saves that in an ARP cache. Okay. And of course, the computer uses as well, it uses ARP to retrieve the MAC address of the router configured as its default gateway. So that there's an IP address that you pop in for your default gateway that says this is how you get out of the network. So if it builds a packet, right, that has a destination outside of its network, it's going to ARP the default gateway to get that MAC address, because it needs to know the MAC address of the gateway to get out of the network. Okay. And of course, we know that the router will strip the frame and put a new frame on as it sends it. So let's look at a real quick transmission from one device to another. Here we have computer 1. You see it's got an IP address and a MAC address, right? We have an IP address and MAC address for our router, IP and MAC address on this destination network. So initially, computer 1 generates a packet. It's trying to communicate with computer 2, right? It's going to generate the packet and say, okay, all right, destination IP address is going to be 172.16.11.5, right? Source IP address 192.168.10.0. I'm sorry, 110. I apologize. So that's your packet now. So source. Sorry for the terrible handwriting here. I'm trying to do this on the screen now so that there's not as much radio silence. But okay, so source IP address, right? This is going to go in the source. This is going to go in the destination. Okay? All right, now when it builds its frame, the frame is going to, first it has to send out an ARP that says who has, so it looks at its IP settings and it finds that the default gateway's IP address is that right there. So it's going to generate an ARP message that says who has this IP address right here, 192.168.100.254. That's what the ARP is saying. Okay, the ARP goes out on the network as a broadcast, and the router replies and it says my MAC address, I have that IP address, my MAC address is 000C85153115B. Okay, so now when it generates the frame, right, this is now your packet, it's encapsulated. Now when we generate the frame, we put a source and destination MAC. Source MAC is going to be the computer's MAC address. Okay, that's going in the source. And then the destination MAC address is going to be the MAC address of the router. Okay, and now we have a trailer added, and there's our frame. Okay, so the frame makes it to the router, right? The router sees it and says, okay, take the frame off. Now I'm going to forward this packet right here, just this information. It forwards that, of course, adds a new frame to it before it forwards it on this WAN. Okay, but then the next router receives it. Okay, and of course ARP might be happening all along this way as well, if there's not already an ARP table for this network on this router. Okay, and then of course this router is going to remove the frame, put a new frame on it, forward it, and then this router is going to receive it and put a new frame on it with the destination MAC address of this computer. Right, the IP address, destination IP address has never changed. The packet traveled the whole way. Okay, this stuff got changed as it went through routers. Right, each router is going to remove that information. Okay, sorry for all the scribbles. Now it looks horrible, but it's kind of hard to do this with a mouse. A little easier to do it on paper. Anyway, that's how it's sort of working, right? So even a router can run ARP. So this router has an ARP table. So if it gets to this, if the packet gets to this router, right, and it says the destination IP address is 172.16.11.5, it says great. I know where that network is. I know how to forward that packet, but I don't know the MAC address of that computer. So it sends out an ARP onto its LAN here, right, the 172.16.11 network, or 172.16.00 network. If I don't know if you're being super particular about it, but and this computer gets that ARP request and says, hey, I have that IP address. Who is 172.16.11.5? That's me. Okay, here's my MAC address, and it sends that back. And the router here will add that to its ARP table for this LAN. Okay, so that's what's happening with ARP in a nutshell. Okay, so ICMP we know. Yeah.
I was just going to get that service.
Oh, do you need it? Hang on one second.
Thank you.
Okay. All right. Sorry about that. Okay, so ICMP. I'm trying to power through this. I have just a few more slides. We're very close. ICMP. ICMP, of course, is used essentially as a tester. It sends... essentially, hey, are you there? between devices. So we know when we send a ping message, it's using ICMP. That's the protocol that's being used. So ICMP has two types of packet: an echo request and an echo reply. It says response, but it's an echo reply. So that's the ICMP reply. So that just says, if I say ping and then type out an IP address, it just sends out to that IP address a packet that says, hey, are you there? And then if a receiving device with that IP address gets it, it's going to process it and go, yeah, I sure am here. Okay, so this type of message is not being processed up through all the layers. It's only going up through the internetwork layer. The internetwork layer is actually responding with the ICMP reply. That's one of a few types of packets, very rare type of protocol that doesn't go all the way up to the application layer. It just goes up to that internetwork layer and says, nope, I'm here, good to go, right? So ICMP is a particularly handy protocol, and of course it functions at the internetwork layer. Okay, and IPsec. IPsec is used with IPv4. We know IPv6 actually has built-in security, so there is no IP security for IPv6 because it's built right in. Encryption happens with IPv6 automatically, where IPsec is essentially designed just to encrypt data, essentially, and have a password or what's known as a pre-shared key configured on either end of a communication to allow a secure link from point A to point B. It's used mostly in situations where very sensitive transmissions are being sent and received. Typically, the typical instance of IPsec, and I know I'm throwing out a term that probably some of you guys won't recognize, but the typical usage of this is in a VPN. VPN is a virtual private network. We're going to talk about VPNs in more detail later on, but IPsec would typically be used in that scenario. That's the most common scenario that you see this used. Okay. So now, I would normally stop the video here and do another one, but because I'm trying to get through this, and this is relatively short, I'm going to talk about network access layer protocols. At this layer, this is where you get a physical address for a network interface. This is what the protocols are responsible for. They're also responsible for identifying incoming frames and addressing outgoing frames, right? This is just, at this point, this is where frames are encapsulated and frames are de-encapsulated at the network access layer, right? This is, when you talk about network access layer protocols, really you're talking about essentially all of chapter 3's information, or not really chapter 3. Network technology, yeah. Chapter 3 is network technologies, right? Where we talked about Ethernet and FDDI and token ring and all these different things, right? That would be protocols that function at the network access layer. It's just different methods for putting data onto a medium. At the end of the day, that's really all it comes down to. Okay, they do provide error correction, very basic error correction for frames, right? And they transmit and receive bit signals, define the signals. Okay, this is all basic stuff that's happening at the network access layer. It's basically the last layer before data gets sent, right? We know a completed frame is what gets translated into ones and zeros and sent as electric signals, light waves, or I'm sorry, light pulses on a fiber optic medium, or radio waves on the airwaves, right? And defines the median connectors. Of course, when you're talking about Ethernet or 10 base T or 100 base TX or 1000 base FX, or you know what I mean, all these different things, those would be defining your network connectors and media, right? So and the speed of your NICs and everything else. So Ethernet functions at this layer. Token ring, FDDI, all the WAN technologies function at this layer, ATM, different things that we haven't really talked about yet in too much detail. Those are network access layer protocols in a way. It's hard to use the term protocols at this point because it's more of technologies and there is some standardization among it, but it's not really talking about languages so much. Though when you're talking about encoding and how data is encoded, yeah, there's a protocol for that. So I guess technically you could call some of those protocols, but it's really more standards and technology that gets utilized. Okay, so network access layer protocols, really it's Ethernet is the most common one that you're going to see in LAN application, and then there's a zillion WAN technologies that are out there that we'll talk about in later chapters. But so far, really the only one that we've really delved into is Ethernet. We've talked a little bit about token ring and a little bit about FTDI, which are a couple of other LAN technologies that are occasionally used. And of course, wireless as well, Wi-Fi, 802.11. So when you're looking at the network access layer, here is an example of an Ethernet frame. Of course, it's got a frame header. This is completed, right? It's got a frame header, and actually it's not, because there's no trailer on here. So there should be a trailer with a CRC, right, to call it a completed frame. But you've got your source and destination MAC address, source and destination IP address, source and destination port numbers, and your data that's actually being transmitted. So all of this is your overhead right here. This is what you're actually trying to get from point A to point B. But this all here is your overhead, right? TCP header, IP header, frame header, if you want to call it a MAC header. There you have it. Okay, that's it. Stopping the recording. And again, I really apologize for not having this up before today. I'll see you guys tonight. Some of you guys I'll see before too long, but I'm going to stop the video and get it up.